I just have no problems with it. I have no problems with it in Pittsburgh where I've been traveling there. Now I'm Pittsburgh places are not doing this stuff. No, for not having the greatest network.
Because they're against
Skills and things.
Let's start. So Elchanan will talk about majority stablest, discrete and SOS.
So this is a continuation of Joe's talk in some sense, and I let him do the hard part, so I'm going to do the easy part. And this is a joint work with Joe and Ninja. He's also here somewhere. Okay. So the first thing I'm going to talk about is I'm going to talk about Borel's result, which Joe already talked about in majority stablest. So we are going to use the same notion of noise stability that Joe was talking about, but we are going to do it both in the discrete cube and in Gaussian space. So let's start in the discrete cube. So in the discrete cube, the noise stability of a function or of a set is the probability that when we take two random vectors x and y that have bitwise correlation rho, they both land in the set. And the Gaussian version is just what we just saw. So now we look at two normal random variables. Each of them is n-dimensional, standard, and the covariance between them is exactly what we've seen at Joe's talk. So the covariance between xi and yi is exactly rho. Then the Gaussian noise stability is just the probability that when you look at these two correlated random Gaussian vectors n and m, they both land at the set F, and that's the stability of the set F. So you can see that these two notions are very, very closely related to each other. There are some examples. This is the dictator set. So the dictator is just you look at one coordinate, deciding if you're inside the set or not. So let's say that if x1 is 1, you're inside the set, and otherwise you're outside the set. So what's the stability of that? Well, you toss your coin, and the probability that the coin lands in the set to begin with is 1/2. Then what's the probability that the second coin lands in the set? This is 1 plus rho over 2, so you get 1 plus rho over 4. Here's a second example. You all know this stuff. So this is the majority function. We have a bunch of, we just look at the balanced majority. So we now want the majority of the bits to be 1. Then we know that there's a result of Shepard from about 110 years ago that says that asymptotically, if the number of bits is going to infinity, then the stability of the majority is approaching this beautiful function, which is 1/4 plus arc sinus rho over 2 pi. Another way of seeing this is considering the Gaussian version of the majority function. So it turns out that the Gaussian version of the majority function is the half space. So you're looking at Rn or just at R, and we're just looking at a set of all vectors where the first coordinate is non-negative. Then it turns out that this Gaussian stability of this set is exactly the same expression. In fact, this is not a coincidence. The limit that Shepard took here in order to prove this result exactly gives you this quantity. Right? So the asymptotic that you get here is the exact formula that you get here. Examples. And should I define what influences are in this workshop? I don't know. So this is the influence. So the influence of majority is small. The influence of dictator is large. So what is Borel's result? So Borel's result is what Joe mentioned in his talk. So this is the example for a set of measure 1/2. So you look at a subset of Rn of measure 1/2. Then the stability of the set is at most this expression, 1/4 plus arc sinus over 2 pi, which is what we saw is the stability of a half space. So this is Borel's result. Now this majority is stablest. So this is something that was proven with Ryan O'Donnell, who is here, and Krzysztof Oleszkiewicz is also here. So this is a discrete version of the same statement. So let me go over it. It's a little bit more complicated if you haven't seen it before. So now we're going to look at the discrete cube. So A is a subset of -1, 1 to the n with the uniform measure. The probability is 1/2. And we want to get a similar bound where now the noise stability is the discrete noise stability. So you want the stability to be at most this expression. However, we have to impose some additional conditions because dictator has bigger stability than this expression. And the condition that turns out to be the useful condition here is we want all of the influence of the set A to be small. So they are going to be smaller than tau. if all of the influences of the set A are smaller than tau, then the stability of the set A is lower than exactly this expression, plus an error epsilon, which depends on tau. Everybody is bored to death? Very good. Okay. So how did we prove it? So when we proved it, what we did is we used Borel result and something which we call nonlinear invariance. But there was something a little disappointing about it. One observation is that the other direction is trivial. If you know the majority is stablest result, this implies immediately by limiting arguments Borel result. And a question which annoyed us since we started thinking about this problem is, can you prove something like that without actually going to Gaussian space? Or in particular, can one give a discrete proof of Borel result? And just to give you a motivation for doing that, if you want to think about in some philosophical level, all of the area of discrete Fourier analysis started because people wanted to prove the hypercontractive estimate in Gaussian space, and they proved it in the discrete cubed in order to get it in Gaussian space. Okay, so everything that we're doing right now, you can think about it as a derivative of the fact that somebody wanted to prove a result in Gaussian space, which was also, in fact, already known. And they said, how would we prove it in Gaussian space? Well, let's find a version of this statement in the discrete space, the space of 2 points. We'll tensorize it. We'll prove it in the space 0, 1 to then, and then we'll get the hypercontractive estimate in 0, 1 to then. And that was the beginning of what we know discrete Fourier analysis. It was used in KKL and so on and so forth. So trying to give discrete versions of Gaussian statements is something that we really like to do. So maybe let me give you one example of a case that this was done before, except for the hypercontractive estimates. So this is the result that also was mentioned in Joe's talk, the Gaussian isoperimetric results. So I won't mention this notion exactly, but in the 70s, Borel and Sudakov and Sigurdsson proved that half spaces minimize the Gaussian surface area. So what do I mean by that? You're looking at Gaussian space. You're looking for a set of measure 1/2. I'm telling you, find for me the set of measure 1/2, which minimizes the Gaussian surface area. And it turns out that the answer for what is the minimizing set is given by half spaces. So again, you can ask exactly the same question that I asked before, and people indeed ask these questions. Can you prove it in the discrete setup? And indeed, Sergei Bobkov in the 90s proved it in the discrete setup. So this should look somewhat familiar to what you've seen in the previous talk. So we're going to be this quantity, the gradient of f squared, which at a point x is just given by the sum over y's, which are neighbors of x, f of I minus fx squared. There's going to be this other quantity, which is I, which is coming sort of from Gaussian's theory, which is I of x is little phi, which is the Gaussian density, and then capital phi inverse, which is the Gaussian CDF, applied to the point x. And what Bobkov proved by induction in the discrete cube, so now we're looking at functions from -1, 1 to the n with the uniform measure to 0, 1, it proved this beautiful functional inequality, that I of the measure of the expected value of the function f is a lower bound to the expected value of the L2 norm of I of f and this gradient of f. If you haven't seen it before, this may look a little scary. I remember the first time I've seen it is when Gil taught a course in discrete Fourier analysis in the Hebrew University in 98 or something. So I saw this and I said, why is this nice? It wasn't clear to me. Okay. One thing that you can get out of it is that if the function takes the value 0s and 1, so you can figure out pretty easily, since the density when you go to -infinity or infinity is 0, you get the following inequality. You get that I of the expected value, or the measure of the set f, is bounded by the expected value of the L2 norm of the gradient of f. Now, the gradient of f for a 0, 1 value function, just, at a specific point, you just measure how many neighbors do you have outside the set, and you take square root of that. So this sounds like a quantity that's related to a boundary, right? It's not necessarily the most natural concept of a boundary that you'd think about, but it sounds like some concept of a boundary. And indeed, it's not hard to see if you do your central limit theorem correctly, that this statement implies pretty easily that for every set in Rn, I of the probability of the set is a lower bound for the surface area of the set, and this inequality is exactly Borel's inequality. It is exactly the Borel and Sudakov-Sigurdsson inequality for the Gaussian surface area of a set. Okay, so again, the philosophy, I didn't explain how you prove this, right? But you see an inequality like that is an equality in minus 1, 1 to the n. It's a function of inequality. You hope you can prove something like that by induction. And if you're Sergei Bobkov, you can prove something like that by induction. Actually, the proof is not so hard if you know what inequality you want to prove. Once you have this inequality, instead of applying it to functions, you apply it to sets. This is a similar philosophy to what we've seen at Jostock. You apply it to sets, you get some more geometric inequality that relates to sets that are subset of 0, 1 to the n. Then when you take the limit, you get the Gaussian result that you were after. Okay. Any questions so far? Okay. So we are going to try to do the same with majority established. So we want to prove the following statement by induction on the dimension. We want to show that if A is a subset of 0, 1 to the n or minus 1, 1 to the n, then the noise stability of A is bounded by this Shepard function plus an error where the error is small if the influences are small. So that's what we want to do. That's what we want to prove by induction. Unfortunately for us, we already know that instead of proving the set version, we should prove a functional version. And since we had this previous work where we knew what the functional version is, it was pretty easy to guess what do we need to prove. So there's this function j that we saw before that satisfies these boundary conditions that at 1, 1, it's 1. And if you have at least one coordinate that is 0, then it's 0. And what we want to prove instead is we want to prove the following inequality. We want to prove that what we've exactly seen at Jostock, we want to prove that the expected value of j is less than j of the expected value. But now, since we know that there are error terms, we expect that there should be some error terms here. This is what we're going to prove. So it sounds very similar to the statement that you've seen in the previous talk. The only difference is now we are looking at the discrete cube. So we're looking at this function from the discrete cube to the interval 0, 1. This matrix, which is exactly the same matrix that we've seen before, it's the matrix of second derivatives, except you multiply by rho the mixed derivatives. If this matrix is negative definite, then the expected value of j of fx, g of y, is upper bounded by j of the expected values plus errors depending on f and g, which are small if the influences are small. That's what we want to prove. Okay, so this is what we're going to prove. So we saw this function before, and if you look at the values 1 half, 1 half, you get exactly the probability that two correlated Gaussians are both going to land in the same half space, which is this expression. Okay, very good. So how do we prove it? Let me actually try to prove it. So we're going to do it by Taylor expansion, which is what James was looking for at the break. So we're going to expand this using Taylor, and we're just going to look at the Taylor expansion of J. So there's going to be a bunch of terms, the zeros terms, the first degree term, the second degree term. We are going to expound around what we're after, which is the expected value of f and the expected value of g. So the zeros terms is just going to be j of the expected value of f and the expected value of g. What is the first order term? Well, the first order term, like in many of these proofs, we're going to use the fact that x and y separately each have expected value 0. So if you look at the first order term, you look at the partial derivative at the expected value, but you multiply that by the expected value of x and by the expected value of y, so you're going to get 0. So the first order term is going to vanish. What about the second order term? Well, the second order term is not so pleasant. It looks like that. So you look at the Hessian and you apply it to xy, xy. So note that there is no rho here. But actually, if you look at this expression, what are you going to get? Well, in the diagonal terms, you are just going to use x, x, and y, y. In the non-diagonal terms, you are going to get expected value of xy here and expected value of xy times here. So you are going to get 1 and 1 on the diagonal, and you are going to get rho and rho over here. So you're going to get exactly the matrix that we've seen before, where you multiply the non-diagonal terms by rho, and now if you want, you can replace the two variables x and y by x and x. Since this matrix is a non-positive definite is a negatively definite matrix, this expression is going to be negative. Okay? So what did we have so far? The zero order term is what we're after. The first order term is 0. The second order term is non-positive. So what we get is we get that the expected value of j of f and g is less or equal to j than the expected value of f and g plus an error, and the error is going to be a third order term. It's going to be involve expected value of f minus the expected value of f to the third power, and similarly for g. Okay? So this is the base case. Now the inductive step is essentially immediate. You don't really have to do anything. So you're going to condition on x1 and y1. You're going to fix them. And if you fix them, you know that once you fixed x and y, x1 and y1, you can just apply the induction hypothesis. So you get exactly this expression, plus the error of order n minus 1 involving the function f and g. And now you're going to apply the base case. This is just a function of one variable, just a variable x1. This is a function of one variable, just a variable y1. So you're going to apply the base case to these functions. And what you're going to get is you're going to get that the expected value of f and g is upper bounded by what you want, plus the expected value of the error of order n minus 1 when you take expectation over x1 and y1, and the expected value of the error of order 1 when you look at the two expectation condition on x1 and y1. So we are just going to call this error epsilon n. So what is this error? So if you write it down, you get a pretty nice expression. So what is fi here? So you have a function f, and many of you know the martingale method. What is the martingale method? You look at a sequence of functions fi where you condition on more and more variables. So f0 is just going to be the expected value of f, f1 is going to be the expected value of f conditioned on the single variable x1, and so on and so forth. You reveal more and more information. So epsilon n f, if you follow the analysis that I've just done, epsilon f of f is just going to be this expression which just look like the martingale difference, except usually when you look at martingale differences, you look at the second power, and here we get the third power. Right? So this tells you that if the differences are small, you are going to expect that this quantity is going to be very small. That's what's going on here. And indeed, if you want to prove Borel result, just from this, just looking at this expression, if you do the standard approximation, what you get is you get that the difference between fi and fi minus 1 when you approximate some continuous function is going to be of order 1 over square root of n. So when you take the third power, it's going to be like n to the minus 3/2. When you sum over all the n variables, you're going to get something that's going to go to 0. So you're going to get to recover Borel's result like that. And unfortunately, similar philosophy applied to if you want to prove the majority is stablest. Unfortunately, again, you have to use hypercontractivity. So why do I say unfortunately? We all like hypercontractivity. The unfortunately comes from the fact that usually when you get hypercontractivity, you get estimates that are not very nice. I mean, you lose something in terms of the dependence of epsilon on tau. Okay, so you get the same loss that there is in all the previous results, which raises the questions if this is indeed necessary. Okay? So now, why is this interesting? It's not clear why is this interesting. You know, we saw various proofs of Borel's result by now. So, as Joe mentioned, there's our result, the previous result, there's the proof of Ryan and Guide for special cases, and there's the proof of Borel, and so on and so forth. So why do we need another proof? So actually, what we've seen in Joe's talk, and maybe what we're going to see right now, is that, you know, extra proofs let you prove extra stuff.
This is the end of the proof?
Yes.
So,
Okay, so I didn't actually. Okay, so the question is, what do you want me to prove? Right? If I want to prove majority is stablest, I have to do some hypercontractive estimates, which either you know how to do or you don't want to see. Okay, it's not very unpleasant. It's a little unpleasant, right?
but I still.
Right. So just a second. So the induction statement is done.
Yeah.
Okay. So this is the inductive statement says that the expected value of j is less or equal than j of the expected value, which was the Gaussian statement, plus an error term. The error term is very explicit. The error term is just given by this martingale difference to the third power. So that's the end of the inductive statement. Now I'm deriving the corollaries of this derivation.
You need some.
Right. So where do influences? So let me try again. Let me try to explain again where influences are coming. So influences are coming in the fact that what you would expect. It's not completely obvious, but what would you expect is that if influence on the function f are small, then these expected values are going to be of some order, and when you take it to a third power, it's going to be much smaller. So it's not going to be concentrated of value close to 1 or minus 1, or 0 or 1. It's going to be somewhat smoothened out because, the function is low influence, so the chances that you're actually going to change is going to be small. To actually argue this rigorously, you need to use hypercontractivity, okay? Because, it could be that the last variable is actually has a lot of influence, right? So once I condition all the variable but one, the last variable typically, it's going to change the value from 0 to 1, right? So the fact that you have a third power and low influences actually means that this expression is small requires a little bit of a proof, which I'm skipping here, okay? But maybe just for the intuition, you can think that one special case of low influence functions is the case where, you try to approximate some Gaussian function, right? So there's some Gaussian function here. I'm trying to approximate it by Boolean functions. How am I going to do it? Each Gaussian random variable I'm going to write as a sum of Bernoulli random variables divided by square root of n. And then what I'm telling you is that when I look at fi minus 1, it's going to be typically of order 1 over square root of n, where n is the total number of variables of the function, or the total number of variables of the function is maybe n times the number of the original functions, variables of the original functions, and when I take the third power, I gain this factor of 1 over square root of n, which means that the error is going to go to 0. Okay? Okay, so that was the end of what I wanted to say about this, and let me tell you a little bit about sum of square proofs, because the organizers asked me to say something about sum of squares proof, so let me do that. So what are sum of squares proofs? So sum of square proofs are proofs that let you prove statements about polynomials. So suppose you have a polynomial of the following form. It's a sum of expression. Each of them is a sum of squares. Each of this is a polynomial. Each of the SIs is polynomial. Time some product sum of polynomials. Each of them is positive in the set that we're looking at. So obviously this polynomial is non-negative, okay, because it's sum of positive expressions multiplied by non-negative expressions, so it's going to be positive. So this is not a very interesting fact. A much more interesting fact is, in some cases, for example, if the set A is compact and the value of a general polynomial is positive on the set, then H can be represented in this form. So let's think about this fact again. So I'm looking at a compact set. I have some general multivariate polynomial that's positive on this set. So I claim that I can write this polynomial in the following form. It's going to be a sum of expression. Each of them is of the following form. This is a sum of square, and this is a product of polynomials. Each of these polynomials is completely positive or completely non-negative on the set that I'm looking at. Okay, so this is a proof that this polynomial is positive, right? I'm giving you a polynomial that's positive. A proof that it's positive is the fact that I can write it in this way. Again, A is the set that is defined by this polynomial. Right, so this is very good. So this is an existential result. So the question is, what do you do with this existential result? Well, one specific case that is interesting is the case where all of the polynomials that we're talking about here on the right-hand side are of degree at most d. Then it turns out that you can actually find this representation in times that is a polynomial in the number of variables n and exponential in the degree d. Okay? So this kind of statements about polynomials are called sum of squares statements or proof for proving that this polynomial is positive. Okay? So why are we doing real algebraic geometry here? Should object to that. So we're doing real algebraic geometry here because the sum of square proofs are very closely related to the Lasserre hierarchy. And this connection recently was highlighted by the work of these people, which start with Barak and ends with Zhu, but I don't remember all the people in the middle, I'm sorry. And then there was a paper of O'Donnell and Zhu. And the connection to the Lasserre hierarchy, which was known before, but was highlighted and much more developed in this two work, is that we can look at the optimization problem. So suppose you want to optimize a function h of x subject to the constraint that it lies in the set, then it turns out that Lasserre hierarchy and the SOS hierarchy are the same, or dual if you want. So the statement that hx is positive on A has a degree d sum of square proof, if and only if it has degree d or d over 2 Lasserre relaxation that gives you a value that is non-negative. Okay, so the two statements are the two ways of looking at this problem are the same or dual of each other. So why is this interesting? Right. So yes. So the history here is involved, and I don't want to offend people, especially dead people, right? So no, I mean this. I mean it's no, but but there are people who are even before. I mean this field has a lot of results, and I'm not sure I know all of the history. This is the statement that I gave right now is definitely not from the recent papers, but it goes back a while ago. I'm not sure who was the first to prove it. Do you know, Ryan? Alexandra, do you know?
When I just read the first.
Right, but it might have been, in the real algebraic geometry community, right? So it's second. I mean, the subject definitely goes to Hilbert problems, but this statement I think goes back to people who are not among us anymore, right? But I'm not exactly sure who are they. Do you remember, Joe? No? Okay. Okay, yeah, we can compare. I mean, there's also the question of how explicit things are, right? So, in some of the math literature, some of the things are not necessarily this explicit. I wish I had more information about it. Like, my student Omer Tamuz has a beautiful saying for this kind of situation. It's amazing that in the past people used to argue about facts. Okay, now you just take Google out and you start looking and you know the answer. It's going to take a little bit of time, but there is a good math survey paper which contains many of the references which we can look at, right? So, yeah, I don't know off the top of my head.
I guess my main question is that in this paper, or is it?
It's the same.
It's the same.
It's the same, yeah, it's the same. There's no, I mean, in terms of
that was my main question. I wasn't trying to find.
Yeah, in terms of the proof system themselves, it's exactly the same proof systems, and it's exactly the same semi-definite or the same semi-definite hierarchies. Okay. Right. So that's the conclusion. So SOS proof shows that LSR relaxation is accurate, and one of the corollaries of what we did is the majority of stablest has a constant degree approximate sum of squares proof. And why is this interesting? Should I prove that to you? Right, I can do what Joe did, which is to tell you that everything is easy. Okay, so I'll just tell you that. So this is easy. We want to show this statement, right, which is, with some error depending on f and g. And what we're going to do, we're going to put it first in dimension 1, and sort of by Putinar or some fancier version of Putinar, any true statement that just involves a finite number of variables, you can prove is an SOS proof. There's a slight technical issue here that j is not actually a polynomial, but you can approximate j by a polynomial, and then you get a true statement. You can get that if you pay a little bit of an epsilon, you can get that the statement is true, and therefore there's a finite degree proof of the statement. And then what you see is what's nice about our proof, and the reason that it didn't work so well for other proofs of majority is tablet, is that the inductive step you can immediately translate to from the normal proof that we had before. Right? So you really don't need to do anything except you have to use hypercontractivity, and for the hypercontractivity, we need to use some of the tools that were already used in Barak and al, and we actually used the papers of Ryan and Ju because it was easier for us to read. Okay, so that's what we were doing.
Are you skimming can be formulated?
Right. Yes. Yes.
So, I mean, here you've done that in a, I mean, you have this pre-majority stablest kind of statement you're trying to prove,
right,
which can conveniently be...
Right, so I agree. Maybe the main advantage of this approach is that you have a statement that is an analytical statement that doesn't talk about 0-1 sets, right? If you want to talk about events that have values 0s and 1, there's no nice polynomial ways of even phrasing them. And the point in what we're having right now is that the statement that we have involves smooth functions, and once you have smooth functions, you can talk about polynomials, right? That's a very good point. So maybe the point is not even the proof, it's just the fact that you have the right statement that involves polynomials, and once you have this right statement, the proof should be easy, even though in our proof, we actually use the fact that it's an inductive proof, so, it gives you an additional power when you actually want to carry it. And like in Joe proofs, when I say that something is immediate, it means that it takes 20 to 30 pages. Okay, so I just want to make this point clear. Okay. So,
but still, why is it
significant to have some square proof?
Very good. Why is it significant to have sum of square proof? So one of the reasons for that is related to hardness of approximation. So everybody is in the room, so in joint work with...
Ask one more.
yeah, of course.
If you have a
The base case is the case of one variable.
can you repeat it?
Yeah. So we want to prove this kind of statement. The point of what we're trying to prove is we want to prove that the degree is bounded as a function of epsilon, the error that we have. Okay? So if you have one variable, it's just a statement about polynomials in one or two variables, right? So it's a statement about a compact set in R2 or something, right? So a statement about a compact set in R2 that involves polynomial approximations of J instead of J. Some version of put in R tells you that this statement must be true. There is a finite degree proof of this statement.
Does that mean that constant?
We'd prove it, but for one variable. For one variable. Who cares about optimization problems with one variable, right? So that's not very interesting on its own.
But is that the dual statement? Is that
Yes,
the equivalent statement?
that's the equivalent.
Constant rounds of Lasserre would do it.
We do it for one variable.
Yeah.
Yeah, so this, it's not an interesting statement on its own, but if you care about the Lasserre hierarchy, that's what it says. And then the other ingredient of what's going on here is, the fact that our proof is an inductive proof and you don't pay too much in terms of the degrees of polynomials, which is something that has to do with the form of the proofs, means that you can go from the one or x and y variables case to the case of many, many variables.
If there is sum of square.
Exactly.
Hierarchy would give you
Right, exactly.
the best possible answer.
Exactly.
And that's why you get an integrality gap.
Or you don't get or you get in small integrality, or you big integrality gap. Yeah. The ratio is going to...
Why the integrality gap is as good as it
As bad as it gets, right? So one of the most confusing thing about this is that what's used to be good you call bad, and what used to be bad you call good. So this is supposed to confuse everybody. Yes.
Can you replace J by polynomial?
Right.
I mean, approximate so that the second order matrix.
Right. So that's when
exactly negative.
Right, so when I said that we're very good, so eventually you squeeze the proof out of me. So when I said that we're using a version of put in R, one of the things I have to deal with the fact that we have to preserve this negative semi-definiteness, but you can do that, right? So, yes, and in particular, there's a version of put in R that shows you that not only if a polynomial is positive, you have a proof of that, but it also shows you that if a matrix is positive semi-definite, there is a proof of that, and we're using a version of this statement in our proof. Yes.
So it will not say anything about the integrality gap in general, right? It will say that for a specific candidate family which was supposed to be a lower bound, it's not a lower bound.
Very good. So thank you, Madhu, for letting me go to the next slide. Okay, so let me go to the next slide. So what's part of the motivation for studying this? So part of the motivation is what's the hardness of max cut. So there's the result with Subash and Guy and Ryan who are all here, where we show that under unique games the hardness is this value 0.878. And in fact, now we are talking, if you were at the talks that in the afternoon yesterday of Madhu and other people, one of the things that you want to do is you want to say, well, if I have hardness in the conditional sense, I also want to have hardness in the unconditional sense, but for weak families of algorithms, like the Lasserre hierarchy or some linear programming hierarchies. So here we're going to talk about semi-definite hierarchies. And indeed, people were considering it even before our result. So Faga and Schechtman show that, the standard algorithm for solving max cut, which is the Gomez-Williamson algorithm, exactly has this gap. Okay, so this is a very strong indication of hardness. And then Kot and Vishnoi construct a different family that also has this gap for a more sophisticated semi-definite program, which involves what's called the triangle inequality, and this is a much harder example. And given these two examples, one may hope that actually you are able to construct examples that, like in Madhu's talk yesterday, actually survive linear rounds of the Lasserre hierarchy or something. And this is not true, and this was already proved in the paper of O'Donnell and Giroux. So they proved that the gap, instead of being, I don't know if to use as good or as bad as 0.878, but it goes up to 0.952 for this example that we used in the Kot and Vishnoi. And to some extent, this is the most, this already shows that we are not getting this kind of picture, at least from the Kot and Vishnoi construction. And I think this result is somewhat less interesting, but our result says that in fact, this example of Kot and Vishnoi has no gap at all, right? So the ratio is 1. So, if you want to amplify it, there's nothing to amplify, right? There's really, this example is not going to survive the Lasserre hierarchy. Okay. Okay. So this is sort of the semi-definite programming part of the story. And I think I ran out of slides, so I'll stop here. Thank you.
Question?
So, in the SOS proof of majority stablest,
Yes.
you have to use the fact that f is a positive value function. It's bounded above by 1.
Right.
So where does that... that wasn't there in the original proof, but only when...
No, definitely, no, in the original, okay, so the original proof, I mean, the functions have to be actually not just positive, they have to be strictly between 0 and 1.
That's
Right.
because you had j and...
Right, and j sort of gets crazy when you get close to 0 and 1. Right, so in fact, in order to control in order to get a good polynomial approximation of the function j, actually you have to, as a function of the epsilon that you're after, you have to truncate the interval a little bit. So it's going to take, it's going to take value between epsilon and 1 minus epsilon, and then there's going to be a good polynomial approximation of the function j. The function j is sort of crazy close to the endpoint 0 and 1.
And you don't care what happens to the polynomial approximation outside?
Outside, right. I mean, we care a lot, but there's nothing we can do about it, right? The function is just crazy, right? Yeah.
Can you go back to the previous
I will
slide?
try.
Yeah, so somehow I didn't understand it at all. I mean, so there is a proof that
But this is a conditional statement. This says that if unique game is hard computation, hardness of max. Now you can ask for a different question. That I have a very powerful family of algorithms, which is all the Lasserre hierarchy algorithms up to level n over log n. Okay, this is a very strong family of algorithms. Let me prove that for this family of algorithms, they all cannot do better than this value. This is the kind of lectures that we had yesterday afternoon. Okay, so for some problems for which there's approximation resistance or hardness of approximation to some factor is known, the same results are carried over to very strong families of algorithms like the Lasserre hierarchy up to linear levels, linear in the number of variables.
So you want to prove it for all these algorithms?
I want to prove it for all these algorithms, but this proves that the best candidate that we had so far for proving such a thing fails.
But you want to prove it for all these algorithms, also assuming unique...
No, again, these are unconditional statements. These are very strong families of algorithms which do not cover everything. Right? They don't allow you to play all kind of combinatorial tricks and so on and so forth. So very strong families of algorithms, and you want to show that these families of algorithms all fail as would be predicted by this hardness result.
And this is not true.
And this is not true. Right, so it's a good contrast to the talk that we've seen in the afternoon yesterday, where hardness of approximation results also held in the hierarchies.
So this O'Donnell Zoo showed it's not true.
Right, exactly.
And what is the...
And we show that it's even more not true.
In what sense?
In the sense that they show, this example still have a gap, right? So,
Show that there's no gap.
there's no gap at all.
So this is for the specific example of Hot and Vishnu.
Which is a very, very smart, if I can say, very, very smart and nice example, and it's the best thing that we can come up with so far.
This example is related to the Gomen's linear conjecture? Or
It's basically identical. It's the same example.
Same example. Okay.
No, but it's not surprising that if you just want to go from the Feige-Shechtman example just by adding one simple-looking inequality...
I didn't say it's surprising, I said it's hard.
No, but then now you are adding so many more inequalities, so it wouldn't be surprising that it would take another 10 years to construct an example. So
No, sure, yeah. But, sorry, this is consistent with what I said. It will take you 10 more years, right? Okay, thank you.